Hello, welcome to the Law of Sines. My name is Tuesday J. Johnson. I'm a lecturer at the University of Texas El Paso and an assistant professor at Doña Ana Community College. This is for pre-calculus. It's Math 1508 at UTEP, Chapter 6, Additional Topics in Trigonometry. Comes to us from Larson's 10th edition calculus text, Section 6.1, Law of Sines. Now, everything we've done in trigonometry so far has involved right triangles, and so the Pythagorean theorem holds, and this and that, and we know a whole bunch of things from those. But there are also acute and obtuse triangles. So if everything we've done so far has been only for right triangles, that leaves out a lot of triangles. So with oblique or obtuse triangles, you need to know the measure of at least one side and two other measures of the triangle, whether it's two sides, two angles, one side and one angle. You have to know at least one side. We can no longer use Pythagorean theorem, so we'll have to have some other techniques. There's four different things that can happen here. We can know two angles and any side. We can know two sides and an angle opposite one of those. And in either of these two cases, we'll use the law of sines, which is in this particular lecture. However, if we know three sides, or two sides and their included angle, so the angle that makes up the two sides, then we'll use the law of cosines, which you can also find on my YouTube channel or linked if you are in my UTEP class. So here we go. The law of sines. And it sounds all formal and everything, but it's super, super straightforward. If I have a triangle, no longer a right triangle necessarily, angle A across from that side A, angle B across from that side B, and angle C, which is no longer guaranteed to be 90 degrees, and across from that side C, then we have A over the sine of A is equal to B over the sine of B, which is equal to C over the sine of C, and we could use any two of these together. We don't have to use all three all the time. And the reciprocals are also equal. So the sine of A over A equals the sine of B over B, equals the sine of C over little side C. If I am solving for a side length, I'll use this top representation. So I always, whatever I'm looking for is in the numerator. If I'm looking for an angle, I'll use this bottom representation where the angle is on top, the sine of the angle. Okay, so let's solve a triangle. And by solving a triangle, it means we want to find the measures of all angles and all sides. We're given that angle C has a measure of 102 degrees, angle B has a measure of 29 degrees, and side B has a measure of 28 feet. Given an angle of 102 degrees and 29 degrees, we know the three angles add to be 180, therefore A must be 49 degrees. Let's get the easiest part out of the way before we start working a little harder. Now I need to find side C. I have information complete for angle B and side B. And so this is going to be my standard ratio, and I'm going to use angle C and side C to form a proportion. That is, side C divided by the sine of 102 degrees equals 28 over the sine of 29 degrees. Law of sine, so we'll use the sine function. In order to find C, I'm going to multiply both sides of this equation by sine of 102 degrees, making sure I'm either in degree mode or making sure to use the degree indicator and staying in radian mode. I can find the value of C with my calculator to be 56.5 feet. Alright, feet. I also need to find side A. In order to find side A, I must use my angle A. Even though it's a found value, we're pretty confident on this one, and we have no choice, no option. We can't use two sides and use the Pythagorean theorem because that only works for right angles, and I don't have any right angles. So, side A over sine of 49 degrees equals 28 over the sine of 29, right? Our standard ratio that we started with as given information. Multiply both sides by the sine of 49 degrees. I'll have A equals 28 sine of 49 degrees over the sine of 29 degrees, which gives me 43.6 feet. 43.6 feet. All right, that's it. We've solved for the 3 missing values using the law of sines. It's not that hard, right? So let's do some word problems. A pole tilts towards the sun at an 8-degree angle from the vertical. So if it's vertical, it tilts towards the sun at 8 degrees. It casts a 22-foot shadow. The angle of elevation from the tip of the shadow to the top of the pole, so if you were laying on the grass looking up at the top of the pole, is 43 degrees. I want to know, how tall is the pole? Well, what I know is, this is 43 degrees. Here, this angle on the ground with the pole makes, this will be 98 degrees. So it's 90 for a right angle, plus 8 degrees tilted off of a vertical, so that's 98 degrees. With 98 degrees and 43 degrees, they all add up to be 180. It tells me that angle B is 39 degrees. Why did I need that? One, I need that because this is the only side length I have. My shadow's 22 feet long. I have to know the angle across from it. And two, when you're stalling, find the easy things to find. Now that we have our value, 22 over the sine of 39, our standard ratio, I want to find the height of the pole. The angle across from that is my 43-degree angle of elevation. So P over sine of 43 degrees is 22 over the sine of 39 degrees. I'm solving for the length of the pole, so I'll use the ratios, the proportion set up with the side lengths in the numerator. Multiply both sides by the sine of 43 degrees. P equals 23.8 feet. So this pole is 23.8 feet. Tilted 8 degrees off of the vertical, casting a 22-foot shadow with a 43-degree angle of elevation to the top of the pole. Everything we need right there. Just make sure you round appropriately based on what your problem specifically asks for. Now, the ambiguous case. If two sides and one opposite angle are given, there are 3 possible situations that can occur. Either no such triangle exists, one such triangle exists, a unique solution which we just saw in the previous 2 examples, or 2 distinct triangles may satisfy the conditions. Due to the uncertainty involved, this is called the ambiguous case of the law of sines. Now, let's break that down a little bit. Consider a triangle in which you're given sides A and B and angle A. So, side A, side B, angle A. I can drop a perpendicular from my angle C. From angle C, this height is given to me by B sine of A, and that's because B is the hypotenuse of this right triangle. We created a right triangle with a H with the height of the triangle, and in doing so, now we can use the sine of A equals height over side length B. Solving for that, height equals B sine of A. So this will tell us how tall our triangle is. If A is an acute angle, right, we have these 4 options, 4 things can happen. If A is less than the height of the triangle, then no triangle exists. We can't reach that wall. That wall is just too short. If A is equal to the height of the triangle, well, then we have this nice little right triangle, and we can use the methods of old. If A, side length A, is greater than or equal to B, well then we have this nice one triangle, and that's how it's going to look. However, if A is bigger than the height, but smaller than B, it's almost like a swinging door. Here's the door jamb, and it swings out here, it swings out here. Which way does A go? And it's hard to tell, and this is our ambiguous case. When A is an acute angle, and A is between the measure of the height and the length of B that is given to us, we'll have 2 possible triangles. If A is obtuse and A is less than or equal to B, we won't reach. And if A is greater than B, everything's good. So if A is obtuse, no problems. It's either none or 1 depending on the measurements we have. If A is acute, we have to pay attention to the value of A. So here's an example of a single solution given side-side angle. For the triangle with A equal 22 inches, B equal 12 inches, and angle A equal 42 degrees, we want to find the remaining side and angles. The first thing we notice is that given angle A, so I'm looking at side A, 22, that's bigger than 12, so we know there's only one possible triangle due to the previous slide. Rewind if you need to take a look at that. We're given side B, so we can now find angle B. If I want to find an angle, angle B, sine of B over 12 equals the sine of 42 degrees over 22. Notice I'm using the reciprocals because I want to find the angle, so I put the angles in the numerators, the sine of the angles. Multiply both sides by 12. This right here, 12 sine of 42, that's B sine of A. This is giving us our height. The sine of B is height over 22. So sine of B is height over 22. That tells me that B is the inverse sine of 12 sine of 42 degrees over 22. And using my calculator in degree mode, I find that that is 21.4 degrees. I'm going to guess that's a 4. I might need to check my calculator to make sure. Sorry about that writing. But we haven't solved for everything yet, right? We have no information at all about angle C or side C. Because of that, we have to use our found value, angle B, of 21.4 degrees, angle A given to us at 42 degrees, to find angle C as 116.6 degrees. Once we know angle C, we can finish by finding the side length C. C over the sine of 116.6 degrees is 22 over the sine of 42. Multiply both sides by the sine of 116.6 degrees, and that will give us 29.4 inches as the length of side C. Next, we'll look at the possibility of no solution using side-side angle. So what we want to show is there is no triangle for which an A of 15, a B of 25, and an angle of 85 degrees. So angle 85 degrees is acute, still less than 90. It's a cute little angle. Across from that, side A has length 15. And adjacent to that, we're going to call side B 25, making angle B down here, and angle C, side C. Here I've drawn in with the dotted red line my height. So I want to check my height. And with this red line, what I'm really looking at is this height is equal to opposite over hypotenuse, right? Because with this dotted red line, we have a nice little right triangle here. So we can still use some of our other techniques, our right triangle techniques. The sine of 85 degrees is height over 25, multiply both sides by 25. The height is 24.9. Well, if it's 24.9 to go from C, angle C, down to base C, then this 15 is not actually reaching. It doesn't reach all the way. It's dangling here in midair. We might say that this part of it, it's not even there. It doesn't even exist. So no such triangle exists, and that's what happens. Our side A is just too short to go along with this big angle of 85. Two solutions. So we want to find two triangles for which little a is 12 meters, little b is 31 meters, and angle A is 20.5 degrees. First thing we do is we check the height, which is B sine of A, and in our triangle, it's right there. I'm checking this height. And B, keep in mind this B sine of A is only if we're given angle A, side B. If I were given side C and angle C and side B, then this would be B sine of C. All right? Keep in mind that this rule is based on the given information with these names. So it'll change based on the name changes as we go along. The height is B sine of A. The B value is 31. Sine of 20.5, that's 10.9. So I know that my A value of 12 is bigger than that. However, my A value of 12 is smaller than B. So I don't know if my 12 goes out from angle C or if it comes back in towards angle B. I don't know if my height is inside or outside of this particular triangle. When that's the case, two such possible triangles exist. Let's find them. So first, I'm given angle A, side A. There's my ratio, sine of 20.5 and 12. I can find angle B. The sine of b over 31 is the sine of 20.5 over 12. Multiply both sides by 31. Sine of b is 31 sine of 20.5 degrees divided by 12, and I could find that decimal if I'd like to. To find angle b, remember that sine is positive in quadrants 1 and 2, right? Sine of b is a positive value. So in quadrant 1, the inverse sine of 0.904702 is 64.8 degrees. So I'll put that 64.8 degrees in quadrant 1, it just is what it is, but I'll also consider it being a possibility. My inverse sine could also be in quadrant 2, right? Inverse sine always lands us in quadrant 1 or quadrant 4, but now we could place the angle b, and we'll call this b prime, the second possibility, the little prime there, is 180 minus the reference angle of 100, which gives me a value of 115.2 degrees. I tell you, I get so confused sometimes, and it's right in front of me when I'm reading it. Now, we have an a value of 20.5 and a b value of 64.8 degrees. We'll leave the b prime for later. Given a and b, I can find angle c, 94.7, due to the fact that the three angles have to add to 180. I know all three of my angles. I know side A, I know side B. I can find side C. Side C over sine of 94.7 degrees is 12 over the sine of 20.5 degrees. Always use as much given information as possible. The side length C will be 34.2 meters. And then we go to the fact that we have an angle A of 20.5 degrees, and we found our second angle B, right? When we did the inverse sine of B, we had an angle in quadrant 1. We just handled that. We put that as a reference angle in quadrant 2, and we got B prime is 115.2 degrees. With this A and B prime, we can find our second possibility for angle C, which is 44.3 degrees. We know little a and little b. We need to find little c prime. Little c prime is sine of 44.3 degrees over the sine of 44.3 degrees equals 12 over the sine of 20.5 degrees. Multiply both sides by the sine of 44.3 degrees. Use a calculator, and I found c prime is 23.9 meters. So I have two triangles. The one on the previous slide, A, B, C, and side length little a, little b, little c. And my second triangle is angles A, B prime, and C prime for the optional second triangle with sides A, B, and little c prime. Notice angle A, side B, and side A are going to be the same for both triangles. And now to the area of an oblique triangle. We had an area formula for right triangles, right? We know that area is 1/2 base times height, but I guess it really does come down to that same thing here. The area of any triangle is 1/2 the product of the lengths of two sides multiplied by the sine of their included angle. What? For any triangle I could possibly draw, one thing we can do is drop a perpendicular. And dropping a perpendicular means this will be a 90-degree angle. If this is A, B, and angle C, then we will have side little c, side little b, and side little a. But more importantly right here, I have half of this length multiplied by the height. Well, what is this height? This height is b sine of a. B sine of a will give me the height, and the 1/2 c, this is my little c right here, half of c gives me my base. So there we go. We have everything we need, and it's different depending on what we have. Which angle do we know? Well, then we need to know the other two side lengths. So if we have angle C, we need to know little a and little b. If we have angle B, we need to know little a and c, and so on. For example, we want to find the area of a triangular lot having two sides of lengths 90 and 52 meters and an included angle of 102 degrees. So regardless of what you want to call these, an angle of 102 degrees, we do not use the side across from that, we use the other two. My area will be 1/2 of 90 times 52 times the sine of 102. Half of 90 is 45. I do a step at a time here. 45 times 52 is 2,340, multiplied by the sine of 102 degrees. And now I'll use a calculator and find that this is 2,288.9 square meters. Notice here, meters times meters gives me meters squared for area. The course for a boat race starts at a point A and proceeds in the direction south 52 degrees to the west to a point B. From the point B, we're going to face south and go 40 degrees to the east to a point C. Finally back to point A. Just so happens that point C lies 8 kilometers directly south of point A. I want to approximate the total distance of this race course. So I know this is the finishing stretch is 8 kilometers. I want to find the length of C and the length of A. Now, approximate the total distance. I know angle A is 52 degrees because that's where I started from. Nice little reference point. If I have two parallel lines, my north-south lines, cut by a transversal, and that's the race course, then alternate interior angles are equal. Therefore, this angle is also 52 degrees. I know this angle is 40 degrees, full 180 degrees here, so I'm going to take 180, subtract the 52 from the alternate interior angles, subtract the 40 from the given information, and I know angle B is 88 degrees. Now, north-south, right, still two parallel lines cut by a transversal. Now my transversal is this side, so alternate interior angles are equal and angle C will be 40 degrees. A little bit of geometry to brighten up your day. I want to find side A. So A over the sine of 52 equals 8 over the sine of 88. Multiply both sides by the sine of 52 and I find that A is 6.3 kilometers. If I want to find, side A, 6.3 kilometers. Side C, C over the sine of 40 degrees equals 8 over the sine of 88 degrees. C equals 8 sine of 40 degrees over the sine of 88 degrees is 5.1 kilometers. Remember, your sketch is always just a basic idea of what's going on, not drawn to scale by any means. Just because A looks shorter doesn't necessarily mean the calculations will lead me to the same conclusion. The total distance, therefore, is 6.3 plus 8 plus 5.1, or 19.4 kilometers. Trigonometry, where we no longer have right angles, still possible, still fairly straightforward. Thanks for listening.